In this video, we will explore electric fields. So what are electric fields? Electric fields are vectors that enable us to determine the electric force on a charge placed anywhere within the field's region. What exactly causes these electric fields? Well, charges do, and we represent those charges using the letter Q. We have both positive charges and we have negative charges. If we have a positive charge, their field lines, the field lines that are associated with that positive charge, move away from the positive charge. If we have a negative charge, then the field lines associated with the negative charge actually point towards the charge, and we're using the dot here to represent the charge. Okay? If we were to have two charges that were different, let's say a positive Q charge and a negative Q charge, what would happen is there would be field lines that would go from the positive charge over to the negative charge. Okay, and so the field line would point from positive over to negative. If we were to have, let's say we had two charges, and those two charges were both of the same charge, let's say both positive, we'd have this charge here and this charge here, both of them being positive Q charges. What would happen in this case is that they would actually repel each other. And so the field lines for this charge and this charge would actually be repelling each other. And since they're both positive in this case, then the field lines will be pointing away from the charge in both cases, and of course the field lines will be repelling each other. If we had both negative charges here, then the only difference here would be then that the arrow would be pointing towards the negative charges, okay, if they were both negative. All right? Okay, so mathematically we can represent the electric field using the equation, or find the electric field for an equation as an equation using E is equal to K, where K is the Coulomb's constant, times Q divided by R squared. Okay, so again, K is Coulomb's constant, Q is charge, and R is actually the distance between the charge and some given point of interest where we're trying to find the electric field at. Okay, K, and this is good to mention, K is actually equal to 9 times 10 to the 9th newtons, approximately anyway, Newton meter square by Coulomb square. Okay, so this is the value of this constant here. All right. Okay, so given all of this, let's say we're asked, and so we have this equation or this problem here, example 1. We want to find the electric field between two, actually, and let's grab a different sheet here. Here we go. This is the sheet I was looking for. We want to find the electric field halfway between 2-point charges. And let's say those 2-point charges are Q1, which happens to have a value of positive 2 microcoulombs, and Q2, which happens to have a value of positive 2 microcoulombs, and they're a distance apart of 1 millimeter. Again, what we're trying to do is find the electric field halfway in between here, so that means we're going to have a distance of 0.5 millimeters here, and then 0.5 millimeters, and that is between these points here. Okay, now, so if this is the case, then in order to find the electric field halfway through there, we would say that, and by the way, I'm going to put the vector sign up here to indicate that this is a vector. E is equal to K, and we're going to find it first for charge number 1. Okay, K Q1 divided by R squared. And we know that to be equal to 9 times 10 to the 9th newtons per Newton times meters square per Coulomb square. And we know that the charge is 2 times 10 to the minus 6 coulombs, and we're dividing that by 0.5 times 10 to the minus third meters square, right? Okay, and if we calculate this out, we end up with, and I already calculated this, we end up with a value of positive 7.2 times 10 to 10th power newtons per coulombs in the x direction. All right, and the reason that it is in the x direction is because, so this is for charge number 1. Remember, it's going away from Q1. So if we start here from the center, that halfway point, then the electric field due to Q1 will actually be going away from that center point. So that's E1, and it will be going in the x direction, and that's why I have the I hat here. Okay, now for E2 we'll have KQ1, or pardon me, KQ2 divided by R squared. Now the thing is when we're calculating for E2, we'd have the same values as up here, so I'm just going to say same as above. Let's go ahead and calculate it out, or write it out. So that's 9 times 10 to the 9th nm squared over c squared times 2 times 10 to the minus 6 coulombs divided by 0.5 times 10 to the minus third meters, and we're going to square that. And of course what we expect then, with we could have the hat here, is that we'll have, and I'll hold off on the sign for a minute, we would end up having a magnitude of 7.2 times 10 to the 10th newtons per coulombs. Now the reason why I held off on the sign here, remember that we're up here where we have the charge, and remember charge is going to be pointing away from the electric field is going to be pointing away from the charge. So for E2, the electric field related to E2 is actually going to be pointing in the negative x direction. Okay, and so because it's pointing in negative x direction, we'll put a negative here, and by the way I forgot my 2. Okay, this is going to be pointing in that direction, and this is going to be in the x, so it's a negative x or negative I hat direction. All right, so now we have both E1 and E2's contribution, if you will, to the electric field at this point. So we can now find the total electric field, which we'll use E, to be equal to E1 plus E2, and don't forget our hats here. But remember, E2 is negative and E1 is positive, and they have the same magnitude, so your net electric force at that point will end up being equal to 0. Okay, the net electric field at that point will end up being equal to 0. All right, so that is our first example. Let's take a look at a second example here. And in this example, we have, well, what we want to find is, we want to find the electric field at some point P, and that point P is right here. Okay, and we have here that the distance between this charge and this charge is the same 1 millimeter, and the distance between this charge and that point P is 1 millimeter. The value here for the charge is plus 2 microcoulombs. You have plus 2 microcoulombs here, and negative 2 microcoulombs for Q3. Okay, so given that this is the case, then based off of our calculation from the first example, E1 hat, or not E1 hat, but E1 the vector, remember, was equal to plus 7.2 times 10 to the 10th newtons per coulombs, and that was pointing in the positive x direction, right? Because going away from E1 here, it's going to be going in the positive x direction because it's going away from E1. Okay. Now we switch the value, or not the value, but the label here. Q2 is in this position, if you remember correctly, right? But now we labeled it as being Q3. So we'll say that E hat, or E vector, for number 3 here, remember that was going the opposite direction, right? And because that was going in the opposite direction, because it was pointing in this direction, or pardon me, remember this is negative, so actually it's not pointing in the positive direction. That is also pointing in the positive direction. It won't be pointing in the negative direction. Okay, so E3 will be pointing in the positive direction because the negative sign, any negative charge, its field, okay, is going to be pointing in the towards it. So E1 was pointing away from it, so that's E1's field line. E2 or E3's field line, since it is negative, is also going to be pointing in this direction, and the reason it's going to be pointing in this direction is because this is negative. Okay, so in that case then we have plus 7.2 times 10 to the 10th newtons per coulombs, and that's also going in the positive direction. Okay, if we add both of those up together, we get the total electric field going in the positive direction, and so that is electric field in the x direction here, 1 plus the electric field 3. All right, and so we end up with adding those two together, both of the components, which are both x components, right? We end up with 14.4 times 10 to the 10th newtons per coulombs. Okay, now if we look at this, we have E2 here that's pointing downward, and we need to take care of that. So that becomes then EY, which is equal to our E2, that's pointing in the negative y direction here, because it's positive and pointing away from it. E2 then is equal to 9 times 10 to the 9th newton meters square coulomb square, 2 times 10 to the minus 6 coulombs divided by 1 times 10, because it's 1 millimeter, right? 1 times 10 to the minus 3 meters, and that's going to be square. I already calculated this out, and so E2 vector, let's make sure we put our vector signs there, is actually equal to 1.8 times 10 to the 10th newtons per coulombs, and this is going to be going in the j direction, but remember it's going in the negative j direction because it's going towards P and going downward. Okay, towards P and downward. So what that means then is that we end up with an E field at that point being equal to the 14.4 times 10 to the 10th newtons per coulombs in the x direction minus 1.8 times 10 to the 10th newtons per coulombs in the j direction. Okay, and that ends up being the answer for this problem. All right, so we've done a couple of examples here. If you need any additional help with this, please do check out my YouTube channel, or you can check out my website at www.clydeletsom.com. Again, that's www.clydeletsom.com.